password on this computer. Okay. So okay, sorry about that. I just had some stuff from last semester I had to delete. Okay, so we got a sorted linked list. So this says, suppose we have a new type of linked list called the sorted linked list, which is a linked list, but keeps all the items sorted. So as a result, when you put an item in, you don't give it an index. You just simply say the item you want to add is this. So our task is to complete the add method for a sorted linked list as shown below. And when you use this, by the way, I'm just gonna send this to everybody in the chat, so you'll be able to use this in the exam if you need it. So this method inserts a new sorted item into the sorted linked list in such a way that the list remains sorted. So for example, if the list is 1, 2, 5, and we do add 4, it's going to become 1, 2, 4, 5, right? It automatically figures out where it needs to go into the list. And by automatically, it means we're going to do it. So we're going to use either a singly or doubly linked list. We can use less than or greater than or equal to compare items. But if you can remember how to use compare to, you can do so for extra credit. You cannot use the add index and e item method. So we can't just simply say, hey, add this at this index, right? You cannot use the get node method, although you might want to rewrite it, and it's got to run in O of n time. In other words, we want to create a fairly new add method. So what I've done over here is I'm going to go ahead and I'll recreate this. So the first thing we need is that I'm going to go ahead and assume that we're working with, do you want me to work with e's or ints first off for this class?
E's.
E's? Okay. So it will be a sorted linked list. So this will make it a bit trickier for me, but hey. So sorted linked list, E item. So node E head, node E tail. So this linked list is, I'm going to say it's got a head, it's got a tail. Okay. And it's got a int size, right? So now we've got to create ourselves our an actual node class for this because, right, we like to, and why do I make these node classes private? I used to not, but other classes we're going to write in this class, class are going to use their own nodes. Like trees will use their own nodes, but they're going to be different. Tree nodes don't have a next and previous, they have a left and right. And possibly a parent, depending on how you write it. So private class, private static class. And basically the static it means it can exist, that nodes can exist without the linked list. You can create a node inside here and it doesn't have to be necessarily attached to linked list or anything. So I think, but point being is that you want to make these static. So now we need an E item, just like anything else, and a previous and a tail. Next, and a node E previous, and I like to keep these simple. The constructor very simple, which is node E item. So here's our constructor, public node E item. It's going to take in an item, and we are going to do this dot item is equal to item. Now there is one small complication though, because this is a sorted linked list, as I've discussed with the is permutation problem we did earlier when we tried to sort it. If we're trying to sort things, they have to be comparable. So I'm going to do something over here that looks a bit weird at first, but I'll help. So what this does is that this enforces that any E's that get passed in are comparables. In other words, they can be sorted. So and that means that now if I have any item over here, like E item, I can do item dot compare to. Oh, except that I have to enforce that this is also the same. This 1 second. And these are the only 2 places we'll need to put E comparable in here. And that's only because I'm using this is a sorted linked list and I'm using E's instead of integers. So now if I go over here, I can say item.compare to, and I can use the compare to method, which again, compare to is useful for sorting anything, because what I'm going to do is I'm going to say, hey, if it's I call these 2 items, if I get a less than result, then the caller is less than the other. If I get a positive result, the caller is greater than the other, and otherwise they're equal to. All right, so we've got ourselves so let's go ahead and figure out how to add this to a linked list. So we need node E item. I am lecturing. I don't know. Is the power drill too loud? I don't think it is. Don't worry about it. They'll let me know if it's an issue. So node E item is equal to new node. Okay, so let's first figure out our base cases here, right? We need some, in other words, let's figure out the really easy stuff for adding this to a sorted linked list, right? So first off, I don't have to worry about, right? So let's compare this to like when we were writing our doubly linked list over here, right? The doubly linked list has 5 cases for when you add, right? Are you out of bounds, adding the very first item, a new head, a new tail, and any other case? And honestly, I like these splitting it up like this because they're the exact same no matter what kind of linked list you're dealing with here. Okay. Now, what if we're adding out of bounds? Do we care about that? Well, it turns out actually no, because the item is, aren't providing an index here, so the index is never going to be out of bounds. So we don't have to worry about that. So the next thing is, all right, we've got adding the very first item, adding a head, a tail, or any other case. And the reason we care about the very first item is because if we don't have any items in here yet, then we don't have a head or tail. So there's nothing to compare to. So if we try to compare to anything, we just fail. So in other words, if this dot size is equal to 0, right? If we don't have anything here, and this is a good time to remind myself, by the way, I should probably put a size ++ over here when I'm done adding. So if the size is equal to 0, what am I going to do? Well, if there's no head or tail, and that means if there's no tail. So this dot size is the same as saying if head and tail are equal to null. Well, then head is going to be equal to adding, and the tail is going to be equal to adding. No comparisons needed. Right? And then we just do the size ++ at the end because that's going to be the true for all the cases. We're going to add the item no matter what. So that's why we put the size ++. Okay. So now what if we want to add a new head? So that's the same as saying, so here in a sorted linked list, the only way that something is going to be the head is that if it's smaller than the current head. So else if it's smaller than the current head. So however, I can't do item is less than, so if I was doing it this way, I'd say if item is less than head.item, if I was using the less than sign. But because I'm using the compare to over here, okay, because I'm going to be using the compare to over here, that's not going to work. Or because we don't know if they're integers or not. Right, they could be strings, and strings can't use that. So how do I do this? Well, I use the compare to. So if item.compare to head.item, if that is, and again, this was kind of if we're doing it for extra credit. Otherwise, if you don't want to use this, just simply remove this and this and change all the e's to integers. That's it. That's all you have to do if you want to use less than or greater than. Right? If you want to use less than or greater than, all we would have to do is remove this, 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 and then turn that into an int, and this into an int, this into an int, and then we could just go and switch this back up. But I don't want to have to undo too many times. So if this is less than 0, boom. So that means that that item should be the new head. So what we're going to do is say adding dot next is equal to adding dot next is equal to head. So we attach this to the head. Head, and since this is, I'm going to assume it's actually, let's see, should I make it doubly linked? Heck no, doubly linked is just pain. It would just be painful to do that. I wouldn't want to do that. So make it easy for myself. Just a next variable. Adding dot next is equal to head. Still going to use a tail though. Adding dot next is equal to head, and then head is equal to adding. And now that node is going to be the first node in the linked list. Okay, so now what if we're adding this to the tail? That would mean that this item is bigger than everything else. That's just a matter of taking this, changing our comparison to tail.item, and then if it's bigger than, let's say if it's greater than or equal to, right? If it's bigger than everything else, that way we can just take care of it right there. If it's the biggest item we've seen so far, then we're just going to tack it onto the end. What we'll say is that tail.next is equal to adding, and then tail is equal to adding. That's it. It's attached now. Okay. Now for the fun part, and by fun I mean fun like being hit on the toe by somebody dropping a hammer on you. Not fun. It's painful in fact. Okay, so else we've got to add something else. So what is our strategy here? Always helps to draw this out. So strategy that we need to use is essentially we've got to have a current, right? So we've got ourselves, we're going to have basically ourselves our sorted linked list. Let's go ahead and say like, and again, singly linked means I have less arrows to draw. And we're going to label this current because that's how we're going to have to iterate through this current. And then we have whatever happened previously, blah, 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 and dot, 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 right? So it goes, because it's going to be somewhere in the middle, right? And then we have adding. And here's what we want to do because we know we're in the middle. And because we know we're never going to be at the tail here, current is never going to equal the tail because we have a condition over here that handles the tail. And so we're going to say, if current dot, so if adding can fit between these two nodes, then put them between these two nodes. So if current can fit between current and current dot next, does that make sense to everybody? So basically what we're going to do is we're going to go item by item, starting at the head and say, hey, if current can fit between here and the guy next to you, then put him in. Makes sense? So if I can show if so, I'll just simply attach this over here and then move this over here and we're all good. So, okay. Easier said than done. What I'm going to do over here is simply say node E current is equal to head. And now I'm going to use while current dot head, sorry, while current dot, not head, that's silly. While current dot next is not equal to null. Now, why current dot next as opposed to current equal to null? And I'm also going to remember to do over here current dot next. Why in the world do I care about this? Why is it current dot next is equal to null versus current is equal to null? Because I want to make sure that the next item after me exists so that I can actually compare the value of this item to the item that exists after current, right? I want to find out if the item fits between these two. The only way it's going to fit between these two is if it's less than the other one. So, and I don't have to check it against current because I already checked it against current by asking, hey, is it less than the head? And if not, well, we're going to start on the head. So kind of convenient. So what that means is essentially I ask if item dot compare to current dot next dot item is less than 0, right? So if item dot is less than the next item, then that's great. That's what we want. Okay, and that's what we want. We want now let's see. So now we need to attach it. So we would say we do adding next equal to current dot next. Which is what I drew earlier. That's that first line. That is just simply saying, hey, whoops, I should not be lazy. I'll go ahead and draw this. Once I'm done with this exam, we'll take a nice long break because I know that we're technically in between our periods right now, but I mean, since we aren't occupying a room, kind of an illusion. So here we've got, right, here's current. We've got adding over here. Oh man, I'm terrible at this drawing stuff. Adding. So current, okay. So what we're doing over there is saying adding dot next is equal to current dot next. And now the next thing we have to do is take this pointer and move it over here, which is just simply saying current dot next is equal to adding. That attaches that. Now, finally, and once that has happened, we don't need to do anything else. So I can just simply break the loop over here. And then we're done. Okay. And that's that problem. The large problem. So again, you're going to be dealing with linked lists over here. So you'll probably be dealing with stuff that imitates a remove method or something like that. Since I did an add method over here, again, you're going to be working with coding sorted linked lists on the exam. That's going to be like 2 questions worth. Okay, final question for the exam, and this will also be the final question on your actual exam or something similar to it. It's going to be worth 20 points, and it's going to be asking you to compare and contrast array lists with linked lists. You will want to use big O notation to talk about this because that is the mathematically precise way to talk about these things. So compare and contrast an array list with linked list. In which one would you want to implement one over another? Okay, so let's go ahead and I don't need to share anymore. Let's go ahead and think about this. How do you compare a linked list to an array list? There are 3 different ways we can analyze this, which is the first way is via memory usage. Okay, in other words, how much memory do they use or abuse or waste? The second way to look at it is how much is their add and remove methods. Now I group add and remove together as one thing because they're reflexive, right? Add and remove rely on the same kind of mechanisms and the same kind of strategies. And finally, get and set. That's our third thing. Okay, so let's start with the easy one, get and set. Okay, get and set. Array lists do their get and set operations in constant time because they're arrays, right? Array lists you can do, again, it works off that mathematical formula, which I was talking about. And basically, for those of you not in the know on that one, which, you know, that's easily possible because it's not necessarily something that is talked about too much, or rather may not have come up in like either of your intro classes. So let's share whiteboard. So if you've got an array here, okay, what am I doing? Drawing, I want to draw this. So suppose we've got an array of whatevers over here, right? And this is int, and this is like an array of whatevers. Let's call them integers for right now. So int r is equal to this big block. What's being stored in R is actually a memory location, like 0f, 1, 2, 3, 4, 5, f. Okay, like that. Okay, so if I want to get, so whenever I ask for like array of like 7, so if I ask for the 8th item in the array or 7th item in the array, it doesn't really, depends on whether you consider this the first or the 0th item, to be honest. So we'll call this, so say you want the item at index 7 in this array. How does it figure it out and get it automatic? Well, the memory location, this is the memory location of this first item, 0, 1, 2, 3, 4, 5, F. That is the memory location of the first item. So to figure out what the, so to figure out how to get 7, the computer just uses the target is equal, so the target memory location is equal to the starting memory location plus size of the thing in the array. Here, actually, I need a bit more space. Ugh, yes, I'm great at this. Okay, so the target memory location, the target that I'm looking for, in this case, the index of 7, it would be equal to the start, which in this case is 0x 1, 2, 3, 4, 5, F, plus the size of thing in array. In this case, it's an int, right? So it would be 32 bits plus, and then over here, it's multiplied by the index, right? Because each of these is taking up an integer's worth of space. So what I would do is just simply, if I want index 7, I would just look 7 integers worth of spaces over from the starting location. And this is something that's very easy for your computer to calculate. How does it do for 2-dimensional arrays? I mean, depending on how it's implemented, I mean, it just becomes a bit more of a complicated operation. Or, I mean, like 2-dimensional arrays are also a lie since everything's just a continuous string of bits, right? So you can just use some fancy dancy arithmetic to figure that out. But the conversion takes, I mean, it's still constant time. Doesn't matter. It's an aside that doesn't matter. Just consider that, I mean, it's irrelevant for these purposes. Point being, it's constant time for us. Okay, constant time for arrays. Now for linked lists, oh well, I'll go ahead and share that screen again because clear, right? For a linked list to find index I, what I have to do is I have to go on that metaphorical scavenger hunt, right? I have to go over here to this node, then to this node, and then to this node, right? So I have to follow this dot next to this dot next to this dot next. And then those things can be in disparate memory locations. I can't calculate it like I did the array. So if I want to look for the ith item, I have to do I nodes, right? And if you see that in the code I write, that means, calling current.next I times. So overall, this takes O of n time, whereas the other one, the array list, was taking constant time, O of 1. Okay. So what about other ways of doing things? So let's talk about adding to an array list. Okay, so if I'm adding to an array list, right, say I want to, what I have to do, so adding and removing is kind of a nuisance in an array list, right? If I want to add to the beginning or end, right, that means I have to make room for it. I have to take whatever's at the end of this and move it over there, and then move that over there and move that over there. I have to move all the items over so that I can make room for the item that I'm adding now. So I can so I can store that item in. Or the reverse, where basically from deleting something, then I take this and move that over there, and overwrite and overwrite and overwrite. Right. But long story short, it takes O of n time, right? And it's the same for if I'm doing it in the middle, except it's n over 2, but that's still O of n. So if I'm adding to the beginning, if I'm adding or removing to the beginning or the middle, it's going to take O of n time. What about to the end? What about to the end? Adding usually to the end of an array list takes constant time because all I'm doing is just simply saying, if I want to add an item over here, ta-da, there was space at the end, so I could add it. However, the exception, and if I remove, it's always constant time to add it there. So constant time to add or remove usually. But if I'm adding, if say like I'm over here and I'm out of space, right, my capacity of the array list is filled up, then I'm in trouble. Because then because what I have to do at that point is that if your capacity for an array list is filled up, what do? You create a new array list twice the size as the old one, copy all n items over to your new array list, and now you go ahead and add another item, which takes a bit of time. Okay. Next. Okay. Now, what about for a linked list, adding or removing? Adding and removing for a linked. So to summarize for the array list, though, if you're adding to the beginning or the middle, or removing from the beginning or middle, it's going to be O of n. If you're adding to the end, it will be constant time, except when you have to reallocate, in which case it would again be linear time. Okay, what about for a linked list? Linked lists are kind of the reverse. Right, if we want to add an item to the beginning or the end, because we know where the beginning of the end is, because we've got a direct pointer there, it's constant time. Doesn't matter how big it is, it's always the same operation, which is simply attach this and make this the new head. Ta-da, we've added a new node. Same with the end. To add a new item to the end, we just simply say, take the last one, point it to the item we want to add, and now this is now the new last node. Ta-da, same, doesn't matter how long. In fact, the manipulation of pointers is always constant time, which sometimes, and some people mistakenly put that all operations are constant time. But that's not the case, because technically while adding the adding process itself is constant time. If you're adding onto the middle, you have to actually find where you're adding first. It takes linear time to get where you're going there. So it's constant time. So constant head or tail, but then it's O of n otherwise. Okay, finally for the last one, memory usage. Okay, so with an array list, it can be wasteful with memory, but if you're cautious with it, it can be very efficient. So first off, right, if I need to reallocate, right, then I'm going to create something twice as big. So say my capacity is 1 million nodes. Sorry, 1 million items. And I add that million in first item. Okay. And then I double that capacity. So that capacity gets doubled to 2 million. So I have 1 million and 1 nodes out of a capacity of 2 million. Now suppose I don't add any other items. Well, that means I'm wasting about half this space over here, 999,000 spaces. And it's 999,999 spaces. And it's gone. So yeah, so array lists can waste memory like that, but there are ways around that. First off, you can create, when you create an array list, whenever you do new array list, you can put a number here. That number is the initial capacity. By default, it's 10, but you can put whatever you want there. And if you know exactly how many items are going to be stuck in that array list, you can just put that there. Otherwise, when you're adding items and you know you're never going to add another item, you can always do like this operation, list.trim, which takes O(n) time. It copies all the items over into an array list, a new array list where, a new internal array where the size is equal to the capacity. The capacity is equal to size, which is convenient. So array lists can waste memory, but you're actually very kind of, it helps because you know how much, because you have operations that enable you to manage that memory if you want to. Linked lists, on the other hand, you have less control over them, but they use exactly as much memory as they're going to say, but they have a bit of an overhead, right? Because not only are they going to be storing the memory location of each item, they also have to store the memory location of next, and they also have to store the memory location of prev. So with an array list, right, each E item is a slot on this array list. Item. So each of these each node basically takes up about 3 times as much space in overhead. I mean, it's not 3 times as much like space period, but only 3 times as much space in overhead, because like this item could be a gigantic item. You know, that item could be massive. It could, and in which case the overhead for storing the memory location, the next and previous, are rather small in comparison, which they usually are. But they use memory and overhead like that. All right. So that last question will be on the exam in some way, shape, or form, where basically I'm asking you to compare and contrast. My advice, come up with an answer for it over the weekend so you can copy paste it into the exam. So I'll stop recording for a second.